Welcome to December 7th LeetCode Challenge. Range sum of BTS. Given the root node of a binary search tree and two integers low and high, return the sum of the values of all nodes with a value in the inclusive range low and high. Low-high. So say we have a binary search tree as such here. We want to find the inclusive sum of low and high. So therefore, we want to basically find that. So basically, 7 and 15. We want to find that the nodes 7 links to. Let's see how to say it. 7 links to 15. By basically having numbers between any number between 7 to 15 are added together. So therefore, 7, 10, and 15 are added together. That's pretty straightforward. You have example number 2 here being low of 6 and high of 10. So any number between 6 and 10 inclusive are added together. We have 6, 7, and 10. They're added together, which equals 23. So the constraints of the nodes are that in the tree are ranged between 1 to 2 times 10 to the 4. The value of each node is between 1 to 10 to the 5. Low and high values are between 1 to 10 to the 5. And all node values are unique. So that's good. So the concept is pretty easy. Just adding every number between low and high inclusive together. The little bit of a tricky part is that it is inside a binary search tree. So in order to do that, you could easily say you could do it recursively, like any other type of tree binary search tree structure. You could do a couple of depth first search, breadth first search. For this one, I'm going to straight up do a stack. So let's have an output to hold the answer. So I'll call it output. And that's going to hold our solution so far. And then our approach is going to be a stack. And that's going to be stack. It's going to be holding root to begin with. And while stack exists, what we're going to do is update a node value to be stack.pop. So we could do it iteratively. So basically what we're going to do is we traverse through the tree using a depth first search. If the node value falls outside the range of low and high, for example, if node.value is less than low, then we know that the only right branch of the node in the value is inside low and high. So how do I say this? The binary search tree it seems to already be kind of have an order, right? You have start from low value, working your way up to high value, and everything's kind of organized in a logical increasing value of order. So we are able to do it iteratively by going through each node, and then basically if the node exists, when we pop it, now we just need to make the comparison. So now we're doing a depth first search through our binary search tree. Then now we just basically compare the value. If it's lowest, let's see, less than or equal to the node.value, and it's less than or equal to high value as well, then it is a value of interest. So therefore, we do output incremented by node.value. So it's within our range. That's good. However, if low is less than node.value, then we could add to the stack append the node.left value. Because we know that if a low value is always going to be on the left of each node leaf. If node dot value is less than the high value, then it's outside our range. Then we also append it to our stack. We're gonna append the node.right this time. Yep. So basically, we pretty much return our answer as such. Let's run this. So this is an iterative approach using a stack. It's kind of mimicking a depth first search. Not truly, but let's submit. Excellent. So we have pretty good runtime and space-time complexity here. So time complexity is big O of n, where n is the number of nodes in the tree. We have basically space complexity of a linear space, or big O of n as well. For the iterative solution we have here, it requires additional space to maintain the stack, so big O of n. Worst case scenario, it occurs when the tree is like in a chain shape, so like linearly. So that means that we have to reach all the way down to the leaf node to find the value. In the case where that's the case, the stack will be big O of n because we have stored at max n number of nodes inside the stack for space complexity. Alright, that's all. Have a great day, guys.